Hello everyone, my name is KUNAL, and today I am presenting my C++ project in front of you, which is ASCII Art generation. So what this project actually does is it prints colorful images on the terminal. So let's see ahead. So what it actually does. So it takes a colorful image, which is usually in the PNG or JPG format, and then prints it on the terminal in the form of ASCII characters. And it prints it in the actual colors, which you can clearly see here that this IIT image is printed here on the terminal. So what we are actually doing in this project, we take an image as an input, then convert the image to an array of pixels, where each and every pixel of the image is converted into an array element. So, and finally, we print the pixels as colorful ASCII characters. So, what problems do we face with direct pixel extraction? So, image file formats are complex. Common formats like PNG, JPEG, BMP, GIF, etc. They are not just raw pixel dumps, but they use compressions, headers, metadata, sometimes color palettes, and whatnot. Then they also have encoding, decoding formats, which make them hard to directly extract pixel data from them. So the common image formats that we use, like PNG, JPG, or JPEG, they are not directly extractable. So for this purpose, to solve the problem of pixel extraction from image, we need to use some libraries like stbimage.h, OpenCV, 3image, libpng, libjpg, etc. Because these libraries have already implemented the parsing plus decoding, which is necessary to break these images into pixels. They handle the edge cases, color spaces, and compression. Writing our own JPG or PNG decoder from scratch is a huge task. So, in this project, we will be using stbimage.h as our library, as it is lightweight, easy to integrate, efficient, and supports multiple image formats. So, what stbimage.h does and how it works? So, the integration of this library is very simple. Just we need to download the .h header file from the GitHub and define it in the hash include. Then we need to call a function of this library called stbi load, and this function will do almost all the work of the pixel extraction from the image and give us it in the form of a character array. We will see that in depth ahead. So now let's get more uh, friendly with the library first. So this function gives us the height, width, and channel of the image along with the pixel data as a character array. As we get the data, we can manipulate the pixels and print them on the terminal window. We will briefly understand the image extraction function ahead, so don't worry. So now from here, our actual coding begins. So first things first, our program begins with the definition of some libraries which we are using, like hash include stbimage.h, hash include iostream string windows.h, and the common namespace using namespace standard, which we use to avoid writing std again and again in front of cout and cin and strings. So to avoid that, we are using namespace standard. And the first line, this is what takes our attention. Hash defined std image implementation. So what this hash defined std image implementation does is this tells the compiler to include the actual implementation of the std image library. This is a popular open source library which we are using to take the data from the image. We will be coming back to this hash define in a while. First gets a bit known with the header files. So hash include stbimage.h. What this line does is this is the header file for stbimage library. It provides the functions needed to read images into memory. Then hash include iostream. We all know that it is used for standard cout and cin for printing and input. Then hash include string, which lets us use the string type for storing text. And then hash include windows.h, a Windows specific library to get the size of the terminal. where we are printing the images on the terminal. So we need to know that what is the size of the terminal, means how many rows and columns it has, so that we can decide how many characters we have to print and in what we have to print and other things. So for that we will be using this library to uh, get the information about the terminal. So let's move ahead. Now what actually is the hash defined in the previous code? This hash defined STB image implementation, which we have written in the first line. So let's see what it is. So the hash define is used here to activate conditional compilation, which generates the actual function codes of the library. So what actually happens is stbimage.h contains both declarations and implementations. Like when we include a header file, it only includes the declarations. But the stbimage is a bit special. It also has the implementations. But the implementation is wrapped in ifdef. Like if there is a macro which tells that if this command is given, then only it will compile that, and then the library code will be written. So when you use hash define HTTP image implementation before including, it compiles the implementation. In other files, if you just use hash include html.h, we only get declarations. So what is the purpose for declaring the both declaration and implementation in this same header file? So its purpose is to prevent multiple definitions like linker errors while keeping the library single header. So what it does is instead of making multiple files, declarations, codes, and which gives some errors while linking and all that, it mixes everything in a single file and wraps the implementation in a hash ifdef, which can be activated by this hash define, and then we can get ahead with this. Used for rendering the image from darkest to lightest. So the first thing we have defined here a string which is A B C D E F. We will be using all these ASCII characters in our code to print the image on the terminal. Like all those pixels will be printed in the form of these ASCII characters A B C D E F. So what this string does is it defines the characters we are going to use for printing the image on the terminal. These characters are darkest to lightest from left to right. Means A will be used for the darkest pixel and F will be used for the lightest pixel, which are chosen on the basis of a formula, which we will see later in this code. Like we are not randomly choosing these characters. We have defined a particular formula for defining the brightness, which is again backed by some scientific efforts. So we'll see that ahead. And here, the main thing to notice is that we have defined it as const, like the string is const, as we don't wish that we should change it anywhere else in the code. And these characters are chosen in such a way that the image looks good after trying multiple combinations. Because if we try some random ASCII characters, the image might not feel that beautiful. But after trying multiple string literals, I have came across this particular combination which makes the image look real and also it feels good. So let's move ahead. Now here our main function begins from the int main. So what basically in we do in the beginning is we just ask the user to enter the file name of the image which he wants to get printed on the terminal. See, here is the string file name. We have see out please enter the file name. It should be in the PNG or JPG format. Like these are the common formats, so we are supporting that. And then we take it as input, the file name. Next, what we do is we load the image using the STB image library. So first we are defining the integers which will be for the image width, height, and the channels. So what this code actually does is it takes the pointers for width, height, channels, and it will store the size of the image and how many color channels it has. Like we will be using three channels for RGB and four channels for RGBA. So what the RGB is generally a red, green, and blue. But what is RGBA? RGBA is red, green, blue, and alpha. So what alpha does is it also defines the transparency of the color. And here you can see we have given 0 at the end as a parameter. So what this 0 does is it tells the STB image library that we want the output image in the original format. We don't want to change it. Like this library also supports that if we have a colorful image, we can change it into grayscale image or some different format. But here giving 0 is the library that we want the image on the original format. So STBI loads the image into the memory and it gives us back a pointer image of the raw pixel data in the form of a character array, which will be explained in depth in later that how and in what type the array is given. Then see, here we have defined a unsigned character array, like unsigned for the purpose like we don't need more memory and we can store more unsigned character array and a pointer to that array. So here STBI load this library takes the file name as an input, then uh, it takes a pointer to the width variable, height variable, channels variable, and the 0 as a parameter at the end to maintain the original image. Each pixel, uh, and then when we get the array, in the array, each pixel is stored as red, green, and blue numbers between 0 and 255. And if the image does not load, or in some cases, if the file is corrupt or in an unsupported format, then we throw an error after checking through if statement that if the image is populated or not. Like if the image is not populated, then this will become uh, this image will remain null or zero, and putting a not symbol before it will make this condition true, and then this C error will run. Like this, what this C error does is it throws out an error. And what the error is could not open the image file. And we return the code -1, it shows that the program failed. Because in this case, we are having an actual failure. As if the image can't be loaded, our program is actually failing because our main task begins from loading the image. Because if the image isn't loaded, we can't print it on the terminal. And here you have gone through this. So let's move ahead. What this does is it takes whole image data and then populates it into a character array in the form of pixels with whole RGB component. And if it's a RGBA image in the form of RGBA component. Then our next task. So the next task is to get the Windows console size, means the terminal size. Why we need the terminal size is because we are printing it on the terminal. So we should be aware of the terminal size before printing it. So then only we can print it properly. So here we have defined a console screen buffer info variable. So what is console screen buffer info? It is a struct provided by Windows Console API, which we have included from that Windows.h file. You remember? So Windows Console API, and then we create a variable CSBI of this type. So what this variable is, it contains all data about the console screen, which is basically our terminal. So what this standard handle does is it is a function which takes a standard output handle as an parameter and returns a handle for a standard output device that is the console Windows output buffer. So here we have the function get console buffer info, which is repopulating our CSBS struct variable, which and this struct variable will contain all the info about the terminal. So we need to provide it a standard handle to the Windows Console API, which is done through this function. And if it succeeds, so it outputs one, and if it fails, it outputs zero. So we handle these cases in the if like mostly it will succeed, but we also need to handle the failure cases. So if it succeeds, then we will run this part of code, and if it will not, then we will run this part of code. So let's see what happens if it succeeds. So first get console buffer string info is a function from Windows API. It takes two arguments, as I told before, pointer to the console string buffer info struct. If successful, it fills the struct which details the console string buffer info and returns a non-zero variable, which is true. And if it fails, it returns zero. And in case of failure, we assume a default terminal size of 120 by 30, which we have already defined here. Like, see, if it fails, because we need to provide some size, and then if it succeeds, then we access the right, left, top, and bottom coordinates, and then we subtract these. Like if we are subtracting right minus left, we will be getting the width, and if we are subtracting top minus bottom, then we will be getting the height. So we are subtracting these parameters and we need to add one. As we know, subtraction removes one row or column, so we need to add one to maintain the exact preciseness in our image printing. And then we get the actual size of the terminal, which we'll be using ahead in our code. So now, one problem that we face is ASCII characters are taller than they are wide. Like, see, here you can see A. It has a, it is of double the height almost as it widths. As ASCII characters are longer than wider, we generally need to set an aspect ratio to maintain the image. Like it is somewhat close to 2. Yeah, it may vary a bit in the range from 1.8 to 2.2, but mostly it's 2. So we print each character twice on the terminal. Now see, what this code does is our next target is to get the target width and aspect ratio. Here, as we have seen before, only we have set the aspect ratio to 2 because of that ASCII characters paradox of the height and width. So now our next target. What this code does is this sets our new width to half of the terminal columns. See this first line. And new width is equal to terminal columns by 2. Why are we setting this to half of the terminal columns? Because we need to print each character twice to maintain the aspect ratio. So for minimum size, this, and then here, like if the image is very small, uh, like it has less than even less than 20 rows. So at least we need to get a bigger image. So that, for that, we are setting the minimum size to 20 if it is less than 20. And by defining an aspect ratio, we define the new height to maintain the image. Like we need to maintain the original aspect ratio of the image, and plus we also need to go ahead with the tragedy of the uh, height and width of the abstract characters. So if the height is bigger than it, here we use a formula like it's a simple ratio and proportion. We are multiplying height by new width by aspect ratio divided by width to maintain the height. Like we are multiplying by aspect ratio as the image is getting wider. So we are our height should also get similarly that much wide. And we are multiplying it by new width and dividing by width to get the new height. It's simple ratio and proportion. And then we are setting like we have done before. If new height is greater than terminal rows, like in this case, if the height is greater than terminal rows, then the image will overflow and we will be not able to see the total image on the terminal. So to calculate that, we are setting a condition here that if new height is greater than terminal rows, then new height equals terminal rows minus 2. And why are we doing minus 2? So that we can leave a little bit of boundary above and below the image so that it does not get cut between that bottom row of the terminal. Let's go ahead. Now what this next line does is it calculates offsets to center the image. Like if the image is smaller and the terminal is bigger, we need to leave some margin here, 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 and in all that way. So then if the image is smaller than the terminal size, then it print measure some padding to left center the image in the terminal. So here for vertical, we have the vertical offset which is terminal rows minus new height divided by 2. Why we are dividing it by 2? We'll divide it by 2 because we will leave half the margin above the terminal, above the image, and half the margin below the image. And the next is horizontal offset. For horizontal, we will be leaving some here and some here. So again, we need to divide it by 2. And here you can again notice the factor of 2 multiplied with the new bit because we are printing each character twice. And then here we begin with our actual printing process. Now we are about to begin the printing of our image. So our first task comes is to print the vertical padding. Now we print some vertical padding from top to center the image vertically. And we don't need to print it from the bottom because automatically it will adjust. No need to print. The image will already end there. So it will get printed automatically at the bottom. So we will be printing horizontal padding until we will be printing horizontal padding while rendering each line before the printing of ASCII characters. So here in the for loop, we are just printing we are iterating the I from 0 to the number of vertical paddings and counting NL so that we get a blank line after each iteration. Next move ahead. Now from here the real rendering of our ASCII art begins. Like this is the part where we will be printing the characters on the terminal. Now till now we have done all the processes like extracting the pixel data from the image, measuring the height, margin, padding, and all that, and getting ready with all the parameters that we require to print the image. Now the real image will get printed on the terminal beginning from here. Like this is a big block of code and a bit complex to understand. So we will be understanding each step of this in smaller blocks. Let's see what does. So initially we begin with a for loop, and this is the overall major for loop in which all other for loops will be nested ahead. So here we begin in a for loop to iterate through all the rows of the image which are equal to new height. Okay. So like our total number of rows is equal to the variable new height, which is showing the number of rows. So we are iterating from 0 to less than new height so that we can go through each row. Initially, you can see here, we print some horizontal padding to center the image horizontally, which is smaller than the terminal size. And here, as you can see, we are printing spaces, we have blank space to center the image if it's smaller than the terminal size. Now, next, moving ahead, we need to understand the array structure of pixel data. Means in what format actually the pixel data is stored in the array. Like suppose we have a 2 by 2 RGB image, which has a width of 2, height of 2, and 3 channels. 3 channels means RGB, red, green, blue only. The array might look like this. We have pixel 1, 2, 3, pixel 0, pixel 1, pixel 2, pixel 3. Because our array indexing begins from 0. So we have these pixels, and then each pixel will have three components of red, green, and blue. So basically, each pixel will be taking three spaces in the array for each red, green, blue character. So while we will be calculating the actual address of a pixel, we will be making jumps of three. See here, I have mentioned that here we multiply by channels. Means here we are doing it by three in this example. But if it has four channels or one or two channels, so we will be multiplying it with the channels so that we can jump correctly to the right pixel. See now the pixel 0 has address like 0 into 2 plus 0 into 3, which starts the image at 0. Then pixel at position 1 comma 0 will be having the address 0 into 2 plus 1. So 3 equals to 3, which will give the position 3 in the array. Then pixel at 0 comma 1. 0 comma 1 will be having the RDX is it's pointing to the actual first color of the pixel. So it will give us this. So this formula overall gives us the position of the exact pixel from where we need to start reading that pixel. Means at the first color of the pixel, like here first color is the red, so it points to the red component of each pixel. So see, here now we have understood the array. We will be implementing that part in a few seconds. Till then, first we need to understand how we are getting the original x and y coordinates. Like here in this for loop, we are running this for loop for each row or pixel by pixel. So now we need to find the original x and y coordinates from the present ones by multiplying with old divided by new. Because see, here we have modified the height and width according to the terminal size. So it makes the coordinates become different from the original, which are just stored in the array. So we need to find the original coordinates, original x and y coordinates of the array to get the pixel data. For this, we define an integer idx here, which points to the index of a particular pixel in an array by multiplying the original y, see here, original y with weight to get the number of rows. Like we will be having an array, we will be having an image, it will have rows and columns. So when we get the original y coordinate and we multiply it by width, see, y coordinate will give us the which row we are in, and width will give us like how many columns we have in that particular row. So if we go to the need to go to the third row, we will be able to skip that much number of pixels because we are using a 1D array here as our library inputs in that format only. Then we will be skipping to that particular row, and in that we will be adding the original x coordinate. What this original x coordinate does is it gives us that particular column number of that pixel. Like here we have reached the particular row using the original y into bit, and now adding original x gives us the original column number of that particular pixel. And then we multiply this whole address with the number of channels. Because as we know, each pixel occupies three spaces in the array because it is a RGB. It can occupy four also, but we are taking the general condition of a colorful image, which is an RGB image. So we multiply it with channels. So if the required number of spaces, because each will be having three spaces, and then we finally get a pointer to the first color, uh, which we will be pointing at that index, and then when we get that, we can move ahead with the ASCII character printing. So let's get ahead. So first thing first, if somebody, it's a common thing, but still, RGB stands for red, green, and blue. Then we try to get the corresponding RGB values for a particular pixel in the array. Like here, all those are differently defined RGB and colors. So we will be accessing them differently by using the IDX and adding 1 and 2 to its all values as they are stored continuously. So here we have seen that in the array it's first red, then green, and then blue. So here we access the image array and put IDX plus 0. 0 means directly IDX address. It uses the red color. And if there are more than, like, see, if there are only one channel, we will be having the red color. There are two channels, then we will be having green, red and green. If there are three channels, then we'll be having red, green, and blue. So here we are using the ternary operator to define this condition, like int green. So green is actually here we are using a ternary operator. Like if number of channels is greater than one, then obviously the green color will exist. And if this condition becomes true, then this part will execute. And if not, then this part will execute. So if number of channels is greater than 1, then green will get the value of IDX plus 1 because green color is stored immediately after red color. And if the it fails. Like we have lesser number of channels, so we will be getting directly red color into the green color. And similarly happens for the blue color. Only thing is here we are adding two because green is stored after red and blue is stored even after green. So from the index of the red, we need to add a 2 to go to the index of blue. And now we are trying to get the exact brightness of the image to determine which ASCII character we need to use to print that particular pixel. So we then use a formula to calculate the brightness of that particular pixel using its RGB components using a special formula. As you can see here, we have used the formula. This formula is derived scientifically as per the brightness section of our eyes to different colors. Like see, our eyes pink as the brightest color, then red is more brighter to our eyes, and then blue is brighter to our eyes. So we have multiplied it with different decimal values to get the exact brightness. And if you will add all these decimal values, they will all add up to 1. And then we are casting it, hence changing this into the type int because we need to get the exact index of the array. For that purpose, we are casting it to int. So int gray uses the brightness of that particular pixel. And on the basis of brightness, we will be selecting that which ASCII character we will use for that particular pixel. So int ASCII index. Now this will give us the ASCII index of that ASCII character. So here we multiply gray with ASCII size minus 1. Why ASCII size minus 1? Because the we will be getting as indexing begins from 0, we will be getting an address less than the total size of the array. And this gray this brightness parameter has a value between 0 to 255, and we need to get it somewhere between this size. So we need to divide this maximum value, which is 255. So we will be getting a particular index between the 0 to the array size. After, as we get the index, we put it here in the here, and we get the particular character. So this is our character choosing part. Now next, this part comes in which we are printing now the exact ASCII character on the terminal in its exact colors with the original RGB components which we have derived from the library. So finally, we have printed the characters on the terminal using the ANSI escape codes. Don't worry, we will talk about them ahead. It's a new concept and I will tell about it in detail. So we give all the RGB color components to see out and print the characters in the original color on the terminal. There you can see we have defined some ANSI escape code, and then we have given the red color, green and blue to the terminal. And one thing to notice here is that we are printing each character twice. We are doing this to maintain the aspect ratio as mentioned earlier. Then finally, after each line, we set the color to default, without which the terminal would have bleed with the colors. So this code, this escape code, set the default color of the terminal. Else the terminal would look mismatched with the colors. It would have got very random. So what are ANSI escape codes and how do they work? So see here, ANSI escape codes helps us to print the ASCII characters in color on the terminal. Let's see. This slash 033 is the escape character in octal, which tells the terminal that text is control sequence, not normal characters. Then this square bracket starts a control sequence introducer or ANSI codes. Means basically from here the ANSI codes start. This told the terminal that it is not normal, it is a control sequence characters. And now this bracket tells that from here we are beginning the control sequence. Now this number 38 is again a escape code. We set the foreground color, that is the text color. Means it tells the terminal that we are setting text color to. Then this And you can notice here that each and every command is separated by a semicolon. Now this two tells the terminal that we want to use 24-bit true color mode, which means that we can specify exact red, green, blue values between 0 to 255. Now this line R slash R angle brackets semicolon G, B, etc. These are the red, green, blue value for the pixels, which we had previously stored in scripts. So now we are providing this to terminal so that we can print exact color. Now this M, at the end we are adding this M. It prints the ANSI escape sequence and applies the color. Means here our command, escape command gets completed and the colors get applied. And now we print each character twice as mentioned earlier. And now this slash 033 and square bracket 0 M, what this does is it sets all formatting back to default. So now next, here we come to the end of our program where we call the function stbi image 3, pass the character array to this function. So what this function actually does is it frees the allocated memory to the character array which was previously storing the pixel data. Like if we don't do this, then there will be memory leaks and the program will end up in something random. So we need to free the memory, and for this we call this function. Now we need to end the program by simply calling our return 0. Now here our coding part ends and now the output part begins. It's still our actual code and now we will be running it. So first, as we are we need to enter the image file. So now we will be printing the image on the terminal. Let's first begin with our image which has shown you earlier. We are typing the image name in the terminal and see here the image gets printed on the terminal in this way. See how beautiful it looks with actual colors and this detail clouds and the building. Everything is printed in detail with exact colors and also see these characters enhances the beauty of this image. Now let's try some another image. I will run the code again and now we will be trying with some beautiful flowers. So let's print flowers.png, which is our file name, and see. Here now the flowers get printed. See the exact colors that the image has maintained, the details and even the brightness. See, yellow colors are more yellow is more bright, blue is less, and all this. So it maintains exact details of the image, pixel by pixel. And at the end, I would like to say thanks for watching my video in the form of again an ASCII printed image. So thank you for watching the video and hope you like it.